Hello students, in the previous section we have discussed parallel plate capacitor as well as spherical capacitor. A third type of capacitor, cylindrical capacitor, is left, right? As I have told you, a cylindrical capacitor will consist of two coaxial cylindrical shells, right? And principle of each and every type of capacitor remains same, that is, when an earth connected uncharged conductor is placed near a charged conductor, then the potential of the charged conductor decreases drastically and accordingly the capacitance increases tremendously. So this forms the principle of each and every type of capacitor. So let's first find out the expression for a cylindrical capacitor, right? These are the two coaxial cylindrical shells of radii A and B respectively. Coaxial means having the same common axis, right? So these are the two coaxial cylindrical shells. Now the inner one is the first one, the outer one is the second one. Now if charge is given on the inner one like this, if charge is given on the inner shell, it is hollow coaxial cylindrical shell. So charge will be residing on its curved surface, right? Negative charge will be induced on its inner face like this. Negative charge will get developed on the inner cylindrical shell of 2, and positive charge will develop on the outer face, which will get neutralized when the second shell is earthen like this. So earth connected uncharged conductor, when placed near a charged conductor, then the potential decreases drastically and accordingly the net capacitance increases tremendously, right? So this is the scenario. So the potential difference between these two is considered to be V, right? Here also electric field is not uniform in this space, and first we are trying to find an expression when the space between the two shells, cylindrical shells, is filled with air or vacuum. We are aware of this formula, C is equal to Q by V. This is a very basic formula applicable for each and every type of conductor or capacitor, right? Now in order to find out the potential difference, we have to make use of this. E in magnitude is given by potential gradient in magnitude. So V is the potential difference between these two, right? Suppose this is a point P. Here we need to find out the potential or potential difference between these two shells. Suppose the distance of this observation point from the axis is R. So dV, it may be written as EdR, or potential difference, it may be written as EdR. Limits will be from A to B. These are the two cylindrical shells across which the potential difference V is to be calculated, right? So this is it. Now students, again I will make a reference to that article, line charge distribution. Here the observation point P lies outside the charged cylindrical shell. So all the charge which otherwise is distributed over its curved surface may be imagined or may be supposed to be considered on this axis. So actually it will behave as line charge distribution, right? So due to line charge distribution, the electric field at a point P, you are aware it's given by lambda over 2 pi epsilon r. Do you remember this? This is the formula for the electric field at a point due to line charge distribution. We have discussed it in the application of Gauss's theorem. So what's the important point is that here observation point P lies outside the cylindrical shell. So all the charge which otherwise is uniformly distributed over its curved surface may be assumed to be concentrated on this axis. So it may be considered to be the case of a line charge distribution. So the electric field will be given by this, and lambda, you are aware, it's given by charge per unit length. If the length of this cylindrical capacitor is L, then E would be given by Q divided by 2 pi epsilon L into R, right? Let's substitute this value over here. So what you get is naught L R dr. Constant term, it can be taken outside the integration. So Q is constant, 2 pi epsilon is constant, the length of the cylindrical shell, that will be constant, A to B 1 by R. R is not constant. If I take observation point over here, the distance from this axis will get changed. So R is not constant, right? So if you solve it, what you get is Q over 2 pi epsilon L, integration of 1 by R with respect to R is natural log of R. It is natural log of R. And limits would be from A to B. Further solving, we get Q over 2 pi epsilon L, upper limit minus lower limit, that is natural log of B minus natural log of A. You can make use of second law of logarithm, which is log m minus log n is log m by n. So potential difference across the two cylindrical shells is given by Q over 2 pi epsilon n natural log of B by A. Put this as equation number 2. So this is the expression for the potential difference, right? Now the last step. Simply you need to substitute this value of V over here. Simply substitute the value of V over here. So this Q and this Q get cancelled. So the formula for the capacitance of a cylindrical capacitor, in case the space between the cylindrical shells is filled with air or vacuum, is given by 2 pi epsilon L divided by natural log of B by A. This is the formula. And this is the natural log. In order to convert natural log into common log, it has to be multiplied by 2.303. So it can be also written in this particular manner. 2 pi epsilon L divided by 2.303 log base 10 B by A. So this is the expression for the capacitance of a cylindrical capacitor, right? So you can easily judge from this particular expression that the capacitance, again, it is depending upon the length, it is depending upon the radius of the cylindrical shells. So what I mean to say is that it does depend upon the dimensions of the conductor under consideration. Also, in case the space between the two cylindrical shells is filled with some medium, then epsilon naught will get replaced by epsilon, which further may be replaced by K times epsilon naught. So here also C medium would be greater than C vacuum. That is, if you consider a parallel plate capacitor, a cylindrical capacitor or a spherical capacitor, whenever some medium is introduced, the net capacitance tends to increase. What I am trying to convince you is that in case of a medium, the expression would be given by 2 pi epsilon L. This will be the absolute permittivity of the medium under consideration. Rest will remain same. Now, K is epsilon divided by epsilon. So, it may be written as 2 pi K times epsilon L divided by 2.303 log base 10 V by A. Compare these two. What do you get? C medium is equal to K times C naught. Again the same thing. Since the dielectric constant of a medium is always greater than 1, therefore the capacitance in the case of medium is greater than in case of air or vacuum. Right? So this is the common conclusion in all the three types of capacitors. So we have discussed three types of capacitors: parallel plate capacitor, spherical capacitor, and last cylindrical capacitor. All depend upon the dimensions, they all depend upon the nature of the medium. In all the cases, C medium is found to be greater than C vacuum. Actually it is K times C vacuum. K is the dielectric constant of the medium under consideration, right? This symbol of a capacitor, whether you are using a parallel plate capacitor, you are using spherical capacitor or cylindrical capacitor, this is the symbol of a capacitor. Set of two parallel lines. This is the symbol of a capacitor. This is the symbol of a capacitor having fixed value of capacitance C. It is the symbol of a capacitor having fixed value of capacitance C. In case of a variable capacitor, the symbol is like this. This is the symbol of a capacitor having varying value of capacitance. That is, the capacitor whose capacitance can be changed, right? So these are the symbols we'll be using while drawing circuit diagrams. Okay, now what we'll do is, let's recollect all those formulas which we have discussed so far, at least for the capacitor. So we have discussed parallel plate capacitor, parallel plate capacitor. Actually, this is the only topic which is in your CBSE curriculum. Rest two are the additional topics which it is advised to do. So its formula is epsilon A by D. This is the formula for the capacitance of a parallel plate capacitor. Second, spherical capacitor. This, we have discussed the capacitance as 4 pi epsilon AB divided by B minus A. Third, just now we have discussed cylindrical capacitor. The formula for cylindrical capacitor is C0 is equal to 2 pi epsilon L divided by 2.303 log base 10 B by A. And in all the three cases, C medium is greater than C value. So these are some very, very important and crucial points in order to understand the next few topics, right? So students, I hope you will go through all these topics thoroughly. And please, if you are really getting benefited, do ask your friends and do share my YouTube channel link with your colleagues and other students as well. And ask them to subscribe the channel and hit the notification button so that whenever I upload a video, it will certainly notify you, right? Thank you. We'll proceed in the next lecture.